Hi, I'm Kashish and today I'm going to explain homework 5 question 2. So this is a question f of x y is equal to 1 upon a y square x, y greater than equal to 1 and x is less than y and it is greater than 1 by y. So the first question is draw the non-zero definition of fxy. So if we had to draw it will look something like this. Anyway, so why does it look something like this? We know that this is the line where x is equal to y. We know that x is greater than 1 by y, and that's why it's the upper half of the graph. But we also know that this line is equal to y is equal to 1 by x, and this curve here. And this particular conjoining point will be 1 because y is greater than or equal to 1, and then this particular half out here, y is greater than or equal to 1, is satisfied by this being we know that this being 1, and x greater than 1 by y is satisfied by this curve here, and it is the upper half of the entire curve. That's why this shaded region is really going to be the non-zero definition of f of x comma y. So that's the first question. The second one says find a so that f of x y is a valid joint density function. So what they really mean by valid joint density function is that when you take the integral, it's equal to 1. So if you were to find this, it would be something like this. So f of x comma y is equal to 1, and then y would go from 1 to infinity, and x as given here on top would go from 1 by y to y, 1 upon a y x squared dx dy, and then you would open up the brackets and solve it, and once you solve it you would basically get 2 into 1 by a is equal to 1, therefore a is equal to 2. So that's how the second part has to be solved. The third part says find and draw the marginal density functions of f of x and f of y. So this is really simple because all you have to do is take out the x component and the y component, or the y component and the x component respectively, for f of x and f of y. So how exactly do you take out the component? So if you had to find f of x, it would be minus infinity to infinity fxy, and then you take out the y component and you'll be left with f of x. So going from minus infinity to infinity, 1 upon ay square x dy. I've left a as it is just in case the part in a is not correct. So 1 by a, 1 upon y square x, going from so now we know that the lower, so now what we have to do here is that we know that the value of x or the value of y will change depending on the value of x. That's why we have two parts of the problem here. So in one case x is greater than 0 and less than 1, and in the other x is greater than 1 and less than infinity. So the limits are put accordingly, and then once you solve it, you will get something like this: f of x is equal to 1 by a for 0 less than x, for x greater than 0 less than 1, and 1 by ax squared for x greater than 1 less than infinity. And then similarly you would solve f of y. So you would just take out the x component, and once you solve it stepwise, you're going to be left with something like this. So obviously in our case a is 2, so 2 and 2 would actually get cancelled and you'd be left with ln y upon y squared. But if you had to leave 2 just the way a just the way it is, then this is what the answer will look like. The last part is verify that f of x and f of y are valid density functions. So if you integrate f of x 1 upon a going from 0 to 1, and 1 upon ax squared going from 1 to infinity, the integration will be equal to 1 without the constant. And if you integrate this, the integration would again be equal to 1 without the constant. So because the integration of f of x and f of y would be equal to 1, we know that f of x and y are valid density functions, and it is shown out here. So that was question 2. Thank you.